Okay. So last class, we talked about pumping lemma, specifically how we can use it to show that certain languages are not regular, right? And then we also saw kind of baby Myhill-Nerode theorem and the toddler version. Okay, so these are, you can basically think of them as tools to show limitations of finite automata, right? So that's what we've been doing with them. We saw the proof of pumping lemma as well, and we saw some applications of it. We saw some applications of MNT, which you couldn't probably get using pumping lemma, okay? And our goal today is to kind of, I'm going to give you maybe more on Myhill-Nerode. Okay, so that's one. And then we're going to jump into our next step, which is Turing machines. Okay. And this is going to be the topic, the main topic really, for the next, I think 6 lectures, right? Okay. And a few announcements. Homework 3 will be up today, as usual, and it's due November 10th. Okay, it mainly has problems on pumping lemma and proving languages are not regular. Okay. All right. So just do a quick recap of what you were talking about. What was the last one? Right. So we were talking about this guy. Okay. And this is another way to show languages are not regular. We saw one example already. Let's do a new example of this. And this is a slightly different language, which is, let's say, palindrome. Okay, so this is a language containing strings which reads the same forwards and backwards, right? Okay. Now, once again, the claim is that this is not a regular language or a function that can be computed by a DFA, NFA, or a regular expression. And I mean, here it's even more puzzling because there is not even counting, right? It's really just about matching the first bit and the second bit, first and the last bit, and the bit from the first, second bit, and the last from the second bit, and so on, right? So for example, we want to say something like 1, 0, 1, 0. Okay, this is a palindrome, right? Okay. And my claim is that this is not a regular language, and I want to use toddler MNT to prove it. So if you want to use Myhill-Nerode theorem, then you want to say, we need to find collection of mutually incompatible strings. Right, so that's our goal. We want to find a collection of mutually incompatible strings. Okay. Any suggestions on what these strings might be? Any guesses? So we need a collection of things so that, let's, if you define f as this function, let me say pal of x equals 1, if x is a palindrome and 0 otherwise. Okay, so you want to check if x reads the same forwards and backwards. Okay, and we want collection of functions which are not equivalent under the palindrome function, which do not look the same to the function. Okay, any suggestions? Yeah.
You had two strings of
Different, sorry.
length.
Yeah, that would work, right? So definitely a good starting point. So let's say I have 0 and 0, 0. Okay. Then clearly these are not in this, these are distinct because I can add a, let's say, oh, actually we have to be, okay, 0, 1, 0. I can add 1, 0 to it. Okay. If I add a suffix of 1, 0, these two things are distinct. Right, so the first one is a palindrome, the other one is not a palindrome. Okay. But this is giving us two strings, right? So to say that a language is not regular, we need to show that no matter how many, whatever number you give me, I can find even more non-equivalent strings, right? So how can I extend this to get more and more strings which are not comparable to each other? Any suggestions? I would say, in some sense, it's actually already here. What would be a way to, so let's say I want 3 strings such that no 3 are comparable, yeah? Yeah, so basically, for example, so let's look at the strings which are 0, 0, 0, 0, 0, 0, all the way up to 0 to the n. Okay, so for every n, we take these strings, and my claim is that all of these are not equivalent to each other. Okay, they are pairwise non-equivalent. So claim 0 to the I is not the same as 0 to the j for I less than j. Okay. And remember, when we have to show that two things are not equivalent, it's a little bit easier because we have to only show the existence of one suffix under which they are not equivalent. Okay. And what would be one suffix that would work here? Any suggestions? Yeah? Either one? Okay, so basically, in some sense, we saw this trick here, right? So we can extrapolate from that. Okay, and the suggestion was, let me do one. So let's say this is my distinguishing suffix, which is I. Okay. And if I put the same thing here, one is a palindrome. The first one is a palindrome. It reads the same front and back, whereas the second one is not a palindrome. Okay. So there are infinite, for any n, there are at least n mutually incomparable strings under palindrome. So by Toddler MNT, palindrome is not regular. Okay. So just if you're using pumping lemma to prove a language is not regular, you need to come up with the right challenge string. In the case of, if you're using MNT, then you have to come up with the right collection of strings. Okay. Depending on the problem, one could be better than the other. In the homework, you'll see one question where you actually cannot prove that it's not regular using pumping lemma because it satisfies the pumping lemma. But nevertheless, it is not a regular function. Okay. So MNT is kind of a more sufficient, is a stronger tool. Okay. And finally, let me state the real Myhill-Nerod theorem, which is kind of the adult version. Okay, we'll not call it that. Right, so the real Myhill-Nerod theorem, it gives you a complete characterization of the best possible finite automata you can have for a function. Okay, imagine I give you a function, maybe it is even regular. If it is regular, you can hand draw maybe, or you design a finite automata for it. But how do you know if it's the best possible? Okay, and MNT can tell you exactly what's the best possible finite automata for a function. So let's have this definition. Okay, for any function, I'm going to define the MNT complexity. I'm just going to write it as MNT of f. It's a number, okay, which is the max k such that there exists k mutually non-equivalent strings. Okay, it's a mouthful, but it's just saying, okay, for your function, what's the largest number of strings that I can find which are not comparable to each other, which are not equivalent to each other under the function? Okay, if it's infinite, then obviously, that's what Toddler MNT was saying, that if I can find more and more and more strings which are all pairwise not equivalent, then the function is not regular. Okay, if it is finite, for example, last class we saw a language where, like, for instance, if I'm trying to do mod 1000, I could find 1000 strings which are all not equivalent to each other. Okay, but it turns out you cannot actually find 1001 strings. 1000 easily, right? And MNT of f is the highest such number if it is finite. It's just notation, if it is finite, then it's MNT of f. Otherwise, we'll just say it's infinite. Okay, does the definition make sense? Yeah. For example, if my function was, let's say, 0, 1 star, 2, 0, 1, f of x equals 1 if number of ones in x is 0 mod 3 and 0 else. Okay. Then I can find 3 strings, 0, 0, 0, 0, or these 3 strings. They're all mutually incomparable. They are mutually not equivalent under this function f. Okay. I can say the same thing for number of ones, right? So I should do ones. I can say the same for this 3 strings. Okay. But I cannot find 4 strings where all 4 pairs are not equivalent to each other. Okay, does it make sense? I can find 3, but I cannot find 4 things. All right. So here it requires some proof, but MNT of f is actually 3. All right. Okay. Now that's a definition. What's the real Myhill-Nerod theorem? Says that for any f Okay. It tells you the exact number of states you need to compute any function if it is computable by a DFA. There is this number, which is the maximum number of strings that I can find so that no two are comparable. And whatever that number is, that's the exact number of states you need to compute that function. Need and suffice to compute that function. Okay. In fact, it also goes to tell you how to draw the transition diagram and so on. But just the fact that there is this precise characterization of the complexity is very nice. Any questions about the statement? Okay. All right. We're not going to prove this. This is kind of, this implies this implies the toddler MNT and the baby MNT that we talked about. Okay. So let me just prove the baby MNT statement, and then we will move on. Where is the baby MNT? Okay. So this is just saying if I can find k mutually non-equivalent strings under F, then any DFA for computing F must have at least k states. Okay. All right. So we use this to prove certain languages are not regular. We use this to say that checking whether, computing the function which checks if the 10th bit from the end is a 1 takes 1024 states. Right? We proved this in the last lecture. Now, any suggestions on how we might prove baby MNT? Like, why is it really true? What is it saying, right? So it's saying somehow, suppose I have this case strings, x1, they could be same length, they could be different length. Doesn't quite matter. Okay, they could be, whatever they are, but they're all pairwise uncomparable, not equivalent under F, right? And given this hypothesis, we want to conclude that any DFA that computes F must have at least k states. Okay. So, why could this be true? Yeah.
It's like for each like xi, there's like some unique set of operations that you like get to satisfy the.
That's a little bit vague. We want to be more precise. So what do we really want to say? We want to say that there is no DFA. So we want to conclude that we want to say there exists no DFA for F with, say, less than or equal to k minus 1 states. Okay. So why is that? It's similar to, why pumping lemma is true. Any guesses? So imagine, we have some DFA that computes F and has a small number of states, right? It has, state, 1, state 2, all the way up to k minus 2 states. Okay, we're assuming they're less than or equal to k minus 1. Okay, and you want to get a contradiction or say that this is not possible. Why? Yeah. Right. That's our assumption. Yeah, that works. You have the same suggestion?
I don't even remember if there's any, but yeah,
Okay.
I know something to do with like the general principle on like the number of states versus like all the different strings, but.
Right. So the idea is that you remember not equivalent says something about whatever you tag along after, right? So no matter what I put afterward, equivalence means that those two things will be the same, right? That's a pretty strong guarantee. But why is that not a big restriction for automata? Because they are, in some sense, memoryless, right? You process a string, you end up in a state, you don't remember anything beyond where you ended up, right? So if two paths kind of led you to the same state, let's say you took string 1010 and then something else, and both of them led you to state number 17. Okay. Whatever comes afterward, both strings will behave the same. Okay. There is this sort of memory collapse that happens in the data, right? Once the states collide, you cannot separate them out. Right? So that's kind of why. So for example, you look at X1, I run my DFA through it, I end up in some place. Okay. I run X2, so let's say X1 ended here. This is, we don't care if it's accept or not accept. I'm just saying X1, when I run it, I end up in this particular state. I hopped around, I'm in state number 0. X2 does its own hopping around, and maybe it ended up somewhere here. Okay. This is where X2 ended. And so on and so forth, right? But now I have K of these strings and only K minus 1 possible endpoints, right? If I send 1,000 people to 999 states, then 2 people must go to the same state. Okay. So, if there exists a DFA with less than or equal to K minus 1 states, then some 2 strings xi comma xj, I is some 2 distinct strings end up at the same state, or let's say lead you. Okay. So what does this mean? Somehow the diagram looks something like this, right? So okay. So maybe my X did something like this. It hopped did all kinds of glorious hops, but then eventually it ended up here. Right? So this is the, path of Xi. Okay, you hop around based on what the input says, but at the end, when you process it, you ended up in state number 18. Okay. And Xj also did something else. It took a completely different path. all roads lead to Rome. Here, at least some two roads lead you to the same state. Okay, you ended up in the same state. Okay, but now this forces f of xi z equals f of xj z for all suffixes c. Okay, because after I process xi and xj, I am in state number 18. Both of them are at the same point. And after that, if you give the same string, they are going to end up with the same trajectory from there. Right? So either both of them will end up in an accept state, or neither of them will end up in an accept state. You cannot have one doing the opposite of that. Okay, so once two things collide, basically at that point, from then on, they are equivalent. Okay. Any questions about this? Right. So, which this is a contradiction as we assumed that xi is not equal to f. Okay. All right. Any questions? Any questions about why you have this nice property of baby MNT? Yeah. Sorry, say it again. Right. So we were assuming that this is not true, that there is a DFA which computes with less than or equal to k minus 1 states, right? And then we concluded that xi and xj, they all have the same exact behavior from the suffix on, right? But this is by definition, this implies that xi is equivalent to f, equivalent to xj under f. Right? That's our definition of equivalence. If no matter what suffix I tag along, you're not able to tell them apart, then the two are equal. Okay? And that's exactly what's happening because they're both starting at the same point. Once you start at this point, you cannot separate them from then on. Okay, so Automata has this very strange restriction that once you collide, you cannot peel them apart afterward with the same input. Yeah?
Okay, so this is all assuming that like the state that they're colliding at is where like xi, I and xj at.
Yeah, that's the end part. So you run xi through the automata, you end up somewhere. You ended up at state number 18. And the same thing for xj. This is kind of the end point where you are after you process xi and xj respectively. Okay, so both end up in the same point, and from then on, you cannot separate them. Okay. All right. Okay. So what did we learn from all of these things? Let's do a quick summary. All right. All right. So first, we are motivated by we want a model that can compute unbounded length inputs. right? And kind of overcame one of the main limitations of circuits and various practical and, let's say, abstraction applications. Okay, so for example, non-determinism, the ability to process regular expressions, all of them come from NFAs, DFAs. It's also, they have some very nice closure properties. Right? Every DFA is closed under ANDs, ORs, NORs. Any NFA can be converted to a DFA and so on. Okay. And we also saw that, okay, as good as they are, they have limitations. Right? So there are many functions, several we saw examples of, that cannot be computed by DFA's NFA. Okay. So that means we need to tweak the model, right? We started out with circuits, which were very good. They could compute anything, but they had a strong limitation that the description size of the function of the circuit had to depend on the input. DFAs got around that, but they're limited in computational power. So now we should ask ourselves, okay, is there kind of a best of both worlds? Can I go beyond this limitation of circuits and of our first unlimited input model, DFAs and NFAs? Okay, so let's talk about that. So to maybe refresh our memory, we kind of arrived at DFAs by saying it's a very simple algorithm, right? So you have the like, imagine the input is written in this way, like an array. And our algorithm is allowed to make a single pass from left to right. And we have fixed memory. Okay, the fixed memory serves two purposes. One, it makes the description length of the machine finite. Okay, so it's not just like I'm limiting the number of units of memory, number of bits that you allow. The reason we really do it is because the number of states has to be limited if I have to describe what you have without looking at the input line. Okay. All right. So let's think of going beyond this. Right? DFAs are good, but not working out. They cannot even compute majority. They cannot compute palindrome. They cannot compute all kinds of other functions, as we've seen. Right? So if you are faced with this issue, what would be some fixes that you would try? Any suggestions? We'll see what we end up with. Yeah. Okay, but I would say that's not quite a solution, because what is certain number? Right? If we say 10 states, again, it's a constant. The whole point is that today you're only interested in 10 seems like a lot. 5 years down the line, it's not a lot. Right? So how do you kind of make a model which doesn't depend on your current limitations? Yeah. The issue is, if I said 10 states, remember 10 states, that seems okay for now, but 10 states is still a small number. 10 is still a number which you're fixing ahead of time. So for example, you might have thought, okay, 512 KB is enough, but now this works, even an email is probably longer. Okay, so you don't want to put an absolute bound, which is, or at least it's not going to fix the issue for us. Okay. Yeah. Okay, so one maybe fix that you can definitely make sense is you can say, okay, allow the head to move left and right. Okay, so one way to think of a DFA is the following, right? So imagine there's like a pointer, right? It's an array. There is a pointer, like a tape head. That's where the terminology head comes from. Back in the day, you actually had tapes and then a head pointing somewhere, right? So you read this first bit, and then you take a jump, right? And then the head moves to the next bit. Okay. You read another bit, you take a jump as dictated by your transition diagram, and then you move one more step. Okay. So there's some hopping that you're doing in the state space, but at the same time, your head, the pointer, is moving from left to right sequentially, right? So you go from here to here to here and so on. Okay. So you're only allowed from left to right, single pass. So this kind of fixes the allow the head condition. Right, so you can now move both left and right. So it's not even a single pass. Maybe you can do multiple passes. Okay. What else would you like to have? Any suggestions? Yeah. Can you assume? Sorry. Yeah, maybe. Okay, so if you think of the DFA as having access to this array, it is reading it. In some sense, it has unlimited read memory compared to its number of states, right? Even if my number of states is 10, I can still process an input which is million bits long. Okay, so you can maybe say allow unlimited memory. Okay, we had to make it precise, right? Because even if you want to allow unlimited memory, our key goal that we really want to fixate on is the description of the machine should not depend on how big your input is. Okay. Anything else? Yeah. Okay, so that's basically allow reads and writes. Okay, so far, in some sense, the DFA has only been reading from the input. Okay, but now I'm also allowing you to write on the input. Okay, what else? Now think of all the bells and whistles that modern architectures have. Let's try and put them into it. Any other things that you might want to add? If it's an array, what is one of the most important operations that you use? Indexing, right? Okay, you can say, why not allow what's called random access. I mean, it's not really random. But the point is, for any array, typically I can say access array position 1000. Then I can say maybe jump to 10,000. I don't have to like go from 1,000, 1,000, and so on. And I can jump directly. What else? Anything else? Yeah, 4 is kind of a stronger version of 1, right? Much stronger. right? Seemingly much stronger at least. Yeah. So you're saying array stuff or? So we have read write, so wouldn't that capture it? Maybe one thing we can add is allow more types of memory. Like, why have only one array? Have 10 arrays, 1,000 arrays, whatever you have. Like, even if you think of any hardware, you have RAM, which is much faster memory, and then you have slower memory, and then all kinds of stuff. Okay. All right. So it turns out that, you can, out of all of these things, we can really capture any form of computation with only two. I guess, the way I wrote it down is these two. Okay. These three will be enough to define a computer and be able to formalize a model and then reason about it, irrespective of any hardware restrictions. Okay. And this was done by Turing, who introduced this model. He didn't call it Turing machine. We call it Turing machine because he did very important work on this. And if you think of a Turing machine, really a one sentence summary is it's a DFA plus a read write memory array. So you'll still have a finite number of states, fixed number of states. Okay. I'm just going to equip a DFA with one long array of read write memory. Okay. Plus a head that can move both ways. Okay. That's it. That's what a Turing machine is going to. Right. And as we will see, surprisingly, these three ingredients are just as powerful as any other machine that you want. Like even my MacBook M1. In fact, it's not going to be much slower either, as we will see. Okay. So let me go over it slowly because it's a bit of a mouthful again to define it, but the ingredients are somewhat intuitive. Yeah.
I guess you're, please.
Okay, so let's get into it. Yeah. So let me talk about the ingredients, the anatomy of a Turing machine. Right? So the first piece that kind of takes it away from the DFA world, or kind of an extension of what we were dealing with in the DFA world, is the presence of a tape, what's called a tape, an unbounded length tape. It starts from some point. This is the starting symbol. Okay. And the tape comes loaded with the input that we are processing on. Okay. It's a very long array, and it starts off with the input written on it, and then everything else is empty. Okay. Really think of it as like a cell where the first n cells are where the input is written, and after that, nothing is. Okay. Makes sense? So that's the first ingredient. So you have one long array. And then you have, just as a DFA, you have a finite number of states. I'm going to use the number k here instead of c as we did before. All right. Okay. And then you have a head that can do three things. One of three things that can move left, right, or stay where it is. So this is L, R, stay. Okay. So imagine, my head starts off here. Yeah, read the first bit. If I were a DFA, I would make a jump and move on to the next bit. Okay. Then I would read the next bit, take a jump on my state space as dictated by my transitions, and then move on to the next bit and so on. Okay. The only difference between that and a Turing machine is the following. It has a very similar mechanism, and the important common point between the two is no matter what's written your entire memory, your memory might already be like gigabits and gigabits, okay? But your current step only depends on what you see literally beneath your feet, okay? Your memory might have many, many things written on it, but you cannot make a decision based on all that's written on it. You cannot scan it. All you can see is very local information. I can see what is written under wherever my head is and what my state is. That's it. Okay? That's how you decouple the size of the memory from the machine. Okay? So no matter how long your memory is, the next step you do can only depend on what you read right beneath your head and what your state is. Okay. Think of state as some kind of processor memory, and then the tape is like hard drive memory that you can look up one bit at a time. Okay. So in words, what does it mean? If at state I and head reads, oops, a symbol A. Okay. So when we go to Turing machines, it becomes more cumbersome to design them only with 0, 1. So we'll allow other alphabet. Again, this is a convenience. You can get rid of it as, if you want to, but it makes things hairier. Change my state to some other state. So just like a DFA, you're at state I, and the head, wherever it is pointing to, reads some symbol. You jump to a new state, whatever that new state is. Okay. And now come the two different things that you do. Okay, this is kind of same as a DFA. The next two steps are unique to Turing machines. You can also write something at the current head position. Okay. So for instance, let's say at some point, my head is pointing here. Okay. I see my state is state number 17. I read a bit 0. It says jump to state number 19. You go there. Okay. But then I am allowed to rewrite what is written. Okay. I'm allowed to rewrite on the memory, but I cannot rewrite anywhere I want or how many ever cells I want. You can only rewrite one location, once again, which is sitting right underneath your head. It's a very local computation, very narrow-minded computation. You see what is on the head, what your state is, you take a jump, maybe rewrite what's on there, and that's it. Okay. The third one, if we had just these two, it would not be so useful. Yeah.
If we had a finite length tape, like, would it be, would there be an equivalency of tape there?
No. The ability to go left and right already breaks. The ability to that you can go both ways, as we will see, that already makes it not a deal. In fact, as you will see, when we design stuff, there are many things, many non-trivial things that you can do here with a small amount of extra memory. Okay. Right. The last piece is, okay, we said I'm allowed to rewrite, but only what is written beneath the head. And then you're allowed the flexibility to move the head. How far can you move it? Again, it's very local. It's severely constrained. I can either go one step to the right, which is what the DFA was doing really, right? But I'm also allowing you to go one step to the left. Or for convenience, we'll say just stay where you are. Okay. So, and then move the head, meaning either to the left. If you're being pedantic, I should be, really speaking, but it's okay. You cannot move beyond the start. Unless you're at the start, you can always move to the left if you want. Okay. And when talking about those things, don't worry too much about the border cases. Pretty much any convention you adopt for them will work. Okay. So don't worry about the border cases. What if I'm at the left edge of the tape? Then let's say you cannot move beyond that. Or you can to the right. Okay. Or you can stay where you are. Right. And lastly, this is again for convenience. I'm also going to allow something which is to just halt computation. It's like an abort, like, okay, I'm done. Now I'm done with the computation. Do whatever you want with the output. Okay. Is the intuitive picture clear? It's a very locally defined computation. There's an array, there is a state. I see what is written on the array underneath the head. I decide which state to jump to. Maybe I rewrite it with something if I want to, and then either take one step to the right, to the left, or stay, or just declare that I'm done, I'm tired. Okay, that's it. These are the things. Yeah?
Okay.
So I would say, the order between these two things, it's good to stick to one convention. Right? You can define it either way. You can say you move and then write, but that I think is less natural than saying I rewrite where I am and then I move. Okay, but either one will actually give you kind of pretty much the same model. Okay, but technically speaking, it can change the operation, right? So whether I move and write or write and move, it's a different operation. It won't change the underlying power, but we'll stick to this just to be very concrete. Yeah. So we'll make it formal. So basically you read whatever you are, and that tells you three actions. So either the state name it has to tell you, the rewriting symbol it has to tell you, and it has to tell you left, right, or stay. Okay. So that's exactly where we are going. That's an excellent question, kind of a good lead up to this. Right? So formally, given what we know about DFAs, you'll see its description is eerily similar with a very small change. So we will have a small number of states. Okay, just as we did for DFA, we had a small number of states. Okay, and think of the states as being 0, 1 through k minus 1. Right? And then you have an alphabet. This is something slightly different from DFAs. In that DFAs, we only had zeros and ones everywhere. Okay, you can do the same thing for Turing machines, but it becomes quite messy and tedious. So we are going to allow some special things. So the alphabet will always have 0, 1. It will also have this weird triangle symbol. This is just to say I'm at the beginning of the tape. It's only reserved for the beginning of the tape. Okay. And then there is also the empty symbol. Okay, meaning a cell is empty. There's nothing written there. All right. So you can have any finite alphabet going into the definition. I might have 10 symbols, 4 symbols. As I said, you can pretty much convert any Turing machine into one where the alphabet is just 0, 1, but it's much easier to design it if you allow yourself more finite alphabet and then do some conversion if you want to. Right? And lastly, the most important piece is, of course, the transition function. All right. So just as for a DFA, the transition function takes a state and a symbol. Now, earlier, the transition function took a state and then input 0 or 1. Now I'm allowing more things, 0, 1, this triangle, empty, maybe allow 4, 5, etc. Doesn't quite matter. And then you do one of few things, right? Just like a DFA, you can jump to a new state. You have to tell me state number 17. If I see a 0, you jump to state number 20. Okay? And you overwrite where you are with some symbol. Okay? And lastly, you have to say, am I going left, right, staying where I am, the head, and or is the entire thing hold? Okay. So this is which state to jump to. What to overwrite. You might not even overwriting, just for convenience, we just say you're always overwriting with the same thing if you're not rewriting it. Okay. And this is what does the head do? Okay. Any questions about the ingredients in a Turing machine? It's just a transition function. Mathematically, is just a function very similar to what we had for a DFA, except in a DFA, we only had this part. Now I'm allowing you to overwrite where you are and to go left, right, stay, or halt. Okay. Any questions about this definition? All right. Okay, so here's the ingenious thing that Turing did. He basically showed that, as we will see in many lectures down, any computer basically boils down to a Turing machine, which is just described by this one transition. Okay, so this is going to be our kind of one model that conquers all other models. All right. Okay. So let's take a 5-minute break. When we come back, we'll see some examples, see what we can do with it, play around with it, and learn properties of this. Okay, so now that we know the pieces that are involved, let's talk about how a Turing machine works. I said in its heart, it's a very simple variant of DFA. So we kind of can figure out what it's supposed to do at least, right? So you have so what does the transition function tell you? You can think of it as some giant table. Right, so you have state name, symbol, then state name, symbol, and direction. Okay, so to describe a Turing machine, I have to say, this is going to be my description of a machine. Right, so you see, oops. It could be something like this. You see state 0, you see 0, maybe you go to state 7, maybe write it with 1 and move to the right. Or you might have something like, I'm in state 1, you see 0, you go to 17, you write it with a 0, so I'm not doing anything, and I go left. Okay, and again, as I said, by definition, if you're at the beginning of the tape and you say left, then you don't fall off the tape, but you just stay where you are. Okay. And so on. Okay, so that's the description of the machine. Now, what do you do with it? Well, you start just like a DFA, you start from some current state, right? So think of this as 0 for the start state. Okay. And you always start with head at x0. Okay. And how does the computation proceed? You run this forever, which is, or at least until you see a halt. Okay, I look up my, so new state, new symbol, comma direction or action from the table. All right, so to describe it, it's really, backwards, but that's fine. Okay, so it's just think of it as a notation. So there's the infinite tape is really given to us as a long array. Okay? The array can go on to infinity on the right side, right? And head denotes where the head currently is. It's kind of the index of where the head is. Okay, so tape of head is whatever you're reading right below the head. And as I insisted several times, the key aspect of the computation is it doesn't depend on the entire array. It only depends on what my internal state of mind or state of the machine is and what's the current symbol that I see beneath my head. Okay? It's a very locally described machine. I would make a very local decision based on what I see directly beneath the head and what my state is. That's it. I cannot look at everything else and decide what to do. Okay. So I look up that information and then read out, okay, what should the new state be? What should the overwriting symbol be? And what direction should the head? Okay. So you just make those things. So you say first, maybe current state is going to be updated. to new state. And the tape head is going to be changed. And so whatever is written on the tape at the head location is being overwritten. So this is to update the state. And this is to rewrite under the head. Right? And the third piece is to decide how the head moves. Okay, so we take an action. If A equals left, then you set head to be max of 0, comma head minus 1. Basically move to the left if you can. If you're at the leftmost point, don't move. You're going to just stay where you are. Okay? And in the same way, if A equals right, then the head just moves to the right. If the action says stay, you just stay. So the head doesn't move anywhere. Okay? And if A says halt, you break out of the loop. Okay? Halt means you're halting the computation, stop the machine. Okay? Any question about what's the machine doing on any input? You read the input, you start from the head written on the input is written on the tape. Start with the head seeing the first bit. Yes, based on your state, you take a jump and then do all of the other things as dictated by the transition machine. All right? Okay. So now that we have the model, I can define input output. So on any input X, if the machine halts, if you ever hit the halt state, meaning you're halting, then the output is whatever is written on the tape until where the head is pointing to. Okay, again, this is a convention. So imagine, I run my machine throughout and I hit the halt state here. Okay, then the output is basically whatever is written until and including where your head is currently. Yeah. Yeah, it can give you multi-bit output now. Okay. For most of the cases, we'll only use 1-bit output, but we can just define it in general anyway. Okay. And again, there are different ways of doing it, but this is one convention. This is the one that's followed in the text, and it just works as well. Wherever you halt, you read from the beginning to that halt, but the head, and that's your output. If there are empty cells, that just means that you skip them. Okay. And if M does not halt at all, I could have a machine which says keep going right, keep going right, keep going right, keep going right. Okay. Formally, it is allowed. In the transition diagram, there's nothing preventing it. There's nothing in the transition function that kind of, at least right now, we don't have any protection against it. Okay. In this case, we just give up and say there is no output. All right. And instead of saying there is no output every time, whenever we have to say, I'm just going to put this perpendicular symbol. That's just to say, okay, we have no output. This has gone into an infinite loop. Right? That's our shorthand for that. It can be a little bit confusing in context, but hopefully it'll be clear. And it's helpful to have this symbol. Otherwise, you have to keep writing down, okay, the machine did not halt, the machine did not halt. Okay. If you see perp symbol, it doesn't mean that's a specific output. It just means that you're basically running forever. Okay. Let's do a very simple example. So I am going to define a Turing machine. The number of states is 1. There is only one state. The alpha beta is also bare minimum. 0, 1, the triangle symbol, and free. The triangle symbol will, it just means that you stay where you are. That's kind of the end of the tape. And the machine, on seeing 0 in state 0, there's only one state, remember, says you're going to be in the same state, but you're going to overwrite with a 1 and then move to the right. Okay. If I see a 1, I'm going to stay where I am, but I'm going to overwrite it with a 0. And I'm going to move to the right again. Okay. If I see an empty symbol, I'm going to, state, there's only one state, so there's nothing to do. I'm not going to overwrite anything, and I'm going to halt. Okay, so that's a machine. Now, what does it do? What's the output of the machine on an input X here? Yeah. It's just a flip of the input, right? Every bit is being flipped, right? If it's a 0, it's going to 1. If I see a 1, it's going to a 0, and so on. It's kind of doing the bitwise flip of the input X. Okay? Very simple function. In a very simple machine, it has only one state, and these 3 equations tell you what to do. Okay? All right. So next, we have a computational model, so I can now say what it means to compute with it. Okay, now I'm going to allow multi-output functions because we can. It doesn't matter for us anymore. So a function takes a binary string as input and outputs another binary string, is computed by a Turing machine M if for all x, the value computed by M is exactly the value of f at that input. Okay, for every x, f of x equals m of x. In particular, this means that the machine should halt at some point. And when it halted, what's written on the tape should exactly match what we want for the function f. Okay? All right. In some sense, we saw how to compute the function which flips every input bit. Now let's do something a little more complicated. It's also a good example because it tells us stuff that we couldn't, shows us how to do stuff that we couldn't do before. Let's consider the majority function. As at least as many ones as zeros and 0 otherwise. Okay. So we say DFS cannot compute it, right? So majority cannot be computed by DFS, right? But it turns out that they can be computed by Turing machines, not too surprising. And let's see exactly how. By Turing machines or TMs. Remember, Turing machines are still very, very primitive, right? I said they're entirely described by this transition function. You're not allowed the ability to have loops, no variables. You cannot have, you cannot jump to random places. You cannot count. At least we don't know how to do that, right? But nevertheless, I'm saying just based on these three aspects, read, update what you see right beneath the head, move left or right, and so on, you can actually compute majority. Okay. Any ideas on how you might be able to do it? Any suggestions for how you might compute majority using such a primitive Turing machine? Think of Turing machine almost like the most basic programming language. You have to tell me what the transitions are, and that's it. And that we want to say can compute majority. Any suggestions? Take some guesses, so what do we have, right? So we have to come up with some states. We have to say how to update them, how to decide to move the head to left or right, and so on. Any guesses? No? Well, okay, if there are no guesses, then I'm not going to tell you the answer yet, but I'm going to show you something, and then hopefully you'll guess from there. Okay. You can see this now. I have here. This is a Turing machine simulator that someone kindly wrote and made it available for all of us for free. Okay. And it's a little bit different than how we work, in that instead of the head moving, the tape moves. I think that's for animation reasons. You had a suggestion? Yeah.
I was just wanting to make a guess that it's like a parentheses checker where like it moves to left until it finds it. It moves one direction until it finds a zero, then like crosses it out, and then like moves one direction until it finds it and crosses it out.
Something like that. Yeah, exactly. Right. So that's an excellent suggestion. So let's say, okay. I'm going to show some machine that I coded up. Okay, so this is the entire transition diagram. It's a little bit tedious, but we can make it modular and figure out. As I said, it's really like even lower level than assembly level coding. That's what a Turing machine is, right? The most primitive form. Okay, and the number of states that I have is 10. The alphabet is basically 0, 1. Underscore is the empty symbol for this particular simulator. And A is just my placeholder. I need one extra symbol other than that. Okay. All right, let's run it. Okay. Okay, speed up, speed up, speed up. Uh-huh. So it stopped with in output as 1. Is that correct? Yes. There are more ones than zeros here. Okay. All right, hold on. Okay, it did compute the right answer again. Okay. So what's the guess for how the Turing machine is going to work now? Yeah? Mm-hmm. Yep. Okay, so hold on, let me get this to work though. 1 second. All right, so let's do one step at a time. So the main idea is the reason we don't have to count is majority is almost like matching stuff, right? I can say, okay, I count the number of ones and check if it's more than the number of zeros, or for every one, for every zero, there should be an equivalent one, right? I pair them up. At some point, if I'm unable to pair up a zero, then there are more zeros than ones. Okay? So we try to match zeros with ones. Okay? And if you have a zero that was unmatched, implies majority of x is 0. Otherwise, majority of x is 1. Okay, that's kind of the high level picture. Now let's break it down. Remember, as I said, it's kind of really low level programming language. You have to describe it in terms of this transition diagram, which might have 10 states or something. We are not going to write it at that final level every time. I'll do it once, and then later on we'll do some higher level stuff. Okay, slightly higher level. Okay. So one idea that was already mentioned is you scan to the right until you find a 0. Okay. So you have your input written on the tape. Keep going to the right until you find a 0. Okay. And if no 0 is found, what should you do? If there is no 0 in your input, what should the output be? 1, right? Basically, there are no zeros, so we are fine. So we have to output 1. We know we have to output 1 at this point, but we have to clean up the tape. Right? Remember, Turing machines have this thing that the output is everything that's on the head, on the tape until the head. Okay? So I'm going to abstract that as clean up the tape and return 1. Okay? And if yes, if a 0 is found, what should I do? If a 0 is found, I should look for a matching 1. Right? But before I go on the look for a matching 1, let me mark off the 0 as something that I've already seen. Right? Otherwise, I might get confused later on. Okay? Mark the 0 as seen. Okay? Mark the 0 as seen just means that I'm going to overwrite the 0 with some other symbol. Right? Like an A was the symbol that I was using. That just meant that I've seen it already. Okay? And I have to now hunt for a 1. Okay? But how do I hunt for a 1? I need to hunt from the beginning. I don't know where the 1 is. Right? So you say go to the start of the tape. scan to the right until you find a 1. If no 1 is found, what should you do? If no 1 is found, then you've seen a 0 but no matching 1, so the output should be 0. Okay, so it's going to be clean up the tape and return 0. If yes, a 1 is found, what should you do? So if you found a 0 that said, okay, go look for a 1, and you found a 1 now, what should you do then? Yeah. Exactly. We should first mark it as 0 so that we don't reuse it later on. So mark the 1 as seen. Okay. And what should we do then? Yeah. Go to the start and start looking for a 0 again, right? You say, go to the start and look for a 0 again. Okay. Even at this level of detail, okay, there's like many steps, but this is still very far from what you can do on a Turing machine, right? Seemingly. Because what does it mean? I'm saying scan to the right until you find a 0. Well, Turing machine can only move 1 step at a time. That's something we have to explain. If no 0 is found, clean up the tape and return 1. I can only move 1 step at a time again. I can only see what is right below me. Okay. Same thing here. Go to the start and look for a 0 again. So you have to go to the start. But then once you hit the start, I have to go look for a 0 again. So how do I encode all of that? Okay. So for this one problem, I'll go into how to do this. And for later on, kind of just to see, how Turing machines are actually working. Okay. Later on, we will just work with kind of saying, okay, it's okay to say scan to the right until you see something. Go to the beginning and do something and so on. Okay. So for example here, this is what my Turing machine is going to look like in detail. Oof. Okay, so this is the input. My head is at the beginning. Okay. And I'm going to give this start state a name just so that we have some, there are only 10 states, but it's good to have some meaningful names here. The first name is QFind0. And the alphabet, as I said, is basically 0, 1, A, the triangle, and the empty symbol. Okay, this A is kind of our scene marker. Okay. When I say QFind0, meaning I'm in the process of looking for a 0, right? If I see a 0, then what should I do? Scan to the right until you find a 0. So I'm trying to find a 0. I found a 0. So then you say, mark the 0 as seen, go to the start of the tape. Okay. So it's just you go start, look for a 1, A, meaning mark it as seen, and move to the left. I'm looking for a 0. I see a 1. What should I do? Is this useful for me? No, right? So you just skip and go to the next step. Okay, so you stay in the same position. You don't overwrite it because you're not doing anything, and move to the right. If I see a symbol A, what should I do? Again, this is something that has already been used up, has already been marked, so I should skip it. Okay, so stay in the same state, keep it the same, go to the right. Right? Lastly, I'm looking for a 0, but I find the empty symbol, meaning I've reached the end of the tape or end of the input on the tape. What should I do then? Yeah. So at this point, we know the output should be 1, right? Because I'm looking for a 0, I haven't found a 0. So you say Q output 1, keep the empty symbol as it is, go to the left. Okay. So in some sense, we are storing the other actions that we have to do into specific states. Okay, so it says go start. Okay, that's what we have to tell you. I have to write down what are the instructions for this. I have to tell you what are the instructions for Q output 1. Its job is to clean up the tape and output 1 no matter where it is. Okay? And so on and so forth. So let me do maybe one more and then I won't write other things. I'll show you the code again. Like for example, let's say Q output 1. If I see a 1, what should I do? There are various ways to do it. But remember, the first task is to clean up the tape, right? I don't want to have some other things on the tape just for, clarity. So I'm going to say output 1, overwrite it with the empty symbol, go to the left. Q output 1 and a 0, same thing, just eat it up. Go to the left. If I see the empty symbol, the marked symbol, eat it up, go to the left. If I reach the leftmost point, then I know that I've cleaned up the tape completely. Now I'll enter Q right 1. You are not allowed to override the triangle anyway, and then go to the right. And lastly, if I'm in this right symbol, I see empty, I'm going to write it as a 1 and halt. Okay, so this is the kind of code that you need to write down to figure out what the Turing machine is doing, right? So you can see these are the instructions. I think here I call Q output 1 as accept. It's the same thing. And then go start, you have to implement in gory detail like this, and then so on and so forth. Okay. But the key thing, as we said, is all you need really is to remember where you are. I mean, or just see what is underneath the head, what your state is, and move left or right. Okay. So if you think of this algorithm, it's kind of inefficient. It goes every time to the left, every time to the right, every time, it can make multiple passes on the input. Okay? But as we will see later in next lecture, this is about as bad as it can get, no matter what complicated function you have. Okay. All right, so when we come back on Wednesday, we'll see more examples of Turing machines and what is their power as compared to everything else that we use.